Welcome back, everyone. Today, we're going to cut right past the usual headlines, past the standard building requirements. We want to focus on the high-level intelligence that's really shaping the built world for decades to come. This is the Architectural Insights with KING-KAMBUF, your daily interdisciplinary mentorship brief for Monday, December 8, 2025.
And our focus today is really on advanced professional conditioning.
Yeah.
We're trying to move beyond just designing for what you need today or, the local codes you have to meet right now. Instead, we're going to focus entirely on mastering what we call anticipatory design.
Right.
The goal here is to give you a critical shortcut to that master level of thinking. We do that by looking at global signals in the architecture, engineering, and construction fields, the AEC industry.
And when you say anticipatory design, you mean you're talking about designing for things that haven't happened yet, like regulations, economic problems, things that haven't even been written down. It's about legal adaptability as much as structural longevity.
Exactly. And this isn't guesswork. It's not about looking into a crystal ball. It's about modeling probability. It's about designing a structure that can legally, structurally, and socially adapt to constraints that are going to materialize 20, maybe 30 years down the line.
So we're treating buildings less like fixed objects and more like resilient systems.
That's the perfect way to put it, resilient systems.
That feels like a huge mental shift.
Yeah.
I mean, you're essentially designing arguments, not just assemblies.
Mm-hmm.
Okay, let's unpack this. Architecture that anticipates constraints. That's our starting point.
Right. So the first critical signal we see in advanced practice is this idea of designing for the regulatory unknown. Standard practice, it sees code compliance as a static target. You meet the current requirements, you get your permit, and you're done. But that whole paradigm is collapsing.
Why now, though? I mean, we've had building codes for 100 years. Why is the target suddenly moving? What's the pressure?
The pressure is the speed of change, technological change, environmental change. It's just accelerating. Governments all over the world, and we're seeing these leading indicators in places like the UK, Singapore, New Zealand. They just can't keep up. So they're starting to prepare what they call adaptive code frameworks.
Okay, so if I'm an engineer in, say, Kansas, what does an adaptive code framework actually look like? How is it fundamentally different from the system I'm used to? Is it a set of triggers or a performance standard?
It's both. It's primarily a performance standard, but it's layered over these contingent triggers. So instead of the code specifying you must use material X, it's going to say something like your building envelope has to maintain a thermal resistance of Y, and it must be capable of adapting to a, say, 30% mandated energy reduction by 2045.
Okay, so the code is specifying the future goal and the building's capacity to change, not just the solution for today.
Exactly. The government is basically signaling, look, we know we're going to need to mandate new things,
Right.
whether that's higher fire ratings because of new materials or enhanced flood resilience due to climate change. And we expect your design today to already have the structural and the spatial bandwidth to absorb those changes.
Which means regulatory foresight isn't a legal afterthought anymore. It's moving into being a core design competency. You have to design the building's flexibility just as rigorously as you design its stability.
Precisely. And this ties directly into how you use the International Building Code's own mechanism for innovation. I'm talking about Section 104.11, Alternative Materials and Methods.
Right.
When an advanced practitioner uses 104.11, they're not just saying, hey, here's an equivalent material. They're submitting a documented, rigorous justification. It's basically a highly persuasive legal and technical brief. You have to demonstrate to the authority having jurisdiction, the AHJ, that your proposed solution meets the intent of the code, especially when it comes to future safety and performance, even if the letter of the current code is very prescriptive.
But hold on, if you're drafting that legal brief, doesn't that fundamentally shift your liability profile as an architect or engineer? I mean, if you argue for an innovative solution based on some future prediction and that future turns out differently, are you on the hook?
That's the million-dollar question. And yes, your liability increases. That's where the high-level intelligence comes in. It's why your documentation has to be absolutely airtight. And you mitigate that risk by explicitly designing in what we call reserve capacity, specifically for these future regulatory pressures.
Okay, let's get granular with that. We usually talk about reserve capacity for, snow loads or wind. What exactly is a future code retrofitting load, and how do you even budget for that?
A future code retrofitting load is the anticipated structural or spatial impact of a probable future rule. Let's take a long-term civic building, a courthouse, a major train station, something that's going to be around for 100 years. We have to look at trends in mechanical systems. Are future fire suppression mandates likely to require, say, whole new, much heavier pipe systems running through the core.
Or what if a future energy code requires massive, centralized energy recovery ventilation units, ERVs that weigh twice as much as today's standard, and that means bigger roof curbs, more reinforcement on that top slab?
Exactly that. Or think about life safety upgrades. If new codes mandate increased structural redundancy for emergency power, maybe dual separate runs of conduit or a whole segregated generator plenum, that requires reserve headroom in your mechanical chases. It requires increased slab capacity for all those distribution systems.
But here's the friction point, right?
Hmm.
Who pays for that extra 20% capacity in the structural core when the client today is demanding maximum value engineering?
And that's the lesson. We have to design arguments based on life cycle cost analysis. We have to prove with data that designing that reserve capacity now, maybe it's an extra 10 inches of floor-to-floor height in a critical zone, or some specific structural hardening around where you think future risers will go, is inherently cheaper. Cheaper and much less disruptive than the mandatory retrofitting that will happen in 25 years.
Because the cost of shutting down a hospital or a courthouse for 6 months to surgically install new systems is astronomical.
It far outweighs the initial expense of what I'd call structural generosity.
Which makes the regulation-ready building design drill such a powerful concept. The challenge is designing a building to absorb these future changes without major demolition. How do you even start designing for an unknown?
You don't focus on the specific unknown, you focus on anticipating the vectors of change. The constraints for this kind of exercise are really crucial. For instance, your structural grid has to anticipate added systems. That might mean your column spacing prioritizes future vertical shafts over the perfect open floor plan for today. And, critically, the life safety upgrades have to be feasible while the building is still occupied.
Maintaining full occupancy during a major life safety upgrade, that's a huge challenge. It means the building's essential services have to be externally accessible, or maybe housed in zones you can completely isolate. Because if you have to tear out fire-rated walls or quarter drill slabs to install new stair pressurization equipment, the building is compromised. You have to shut it down.
Right. So the design requires these reserve zones, things like increased floor-to-floor height above the ceiling grids or accessible utility trenches that are totally separate from load-bearing walls. You're not just designing for the building, you're designing for the future maintenance crew. You're ensuring they can perform major structural or system surgery without disrupting the daily life of the occupants. It's an exercise in structural altruism, really.
Okay, now let's put this to the ultimate test, the leadership test. Let's talk about the code change scenario. We have a municipal building. It's at 62% completion. That's that critical phase where all your long-lead materials are bought, they're on site, maybe even installed, and boom, a newly adopted fire code amendment hits. It affects stair pressurization, it affects fire ratings, tight schedule, tight budget, an instant crisis.
And this is exactly where a professional workflow strategy defines leadership. The knee-jerk reaction is to halt construction, panic, and start talking about budget deficits. The advanced professional strategy is a very meticulous 5-step process for mitigation and, importantly, for negotiation.
Walk us through that. What's the workflow that mitigates a disaster like that?
Step 1 is immediate surgical triage. You have to identify the exact scope of the impact. Precision here is everything. You must isolate precisely which construction packages, which subcontracts, which timelines are specifically affected by this one amendment. If the new rule is about stair pressurization, does it really impact the whole HVAC system or just the fan sizing and the ductwork in the vertical risers? You have to minimize the perceived scope.
And if you can isolate the impact, then the engineer's challenge becomes finding an alternative that meets the new rule without having to do radical demolition.
Which leads directly to step 2, developing equivalency analyses. This is where you apply IBC 104.11 in an emergency situation. Can we propose an alternative? Maybe it's a slightly different type of smoke management system or a superior fire-rated paint or assembly that meets the performance intent of the new code without ripping out what's already built. You're literally negotiating with engineering excellence.
So an example would be, instead of installing a newly required larger duct system, maybe you install a highly sensitive early warning system with some localized suppression. And you argue that system provides an equivalent or maybe even superior life safety outcome.
Precisely. Which brings you to step 3, proposing phased compliance options. Look, If full immediate compliance is financially or physically impossible within the current completion window, you have to get creative. You propose phasing the required work over, say, the first 2 years post-occupancy. You secure temporary waivers or a temporary certificate of occupancy based on interim safety measures. This requires convincing both the owner and the AHJ that your transition plan is robust and safe.
And that leads to step 4, which is all about the relationship, coordinating AHJ negotiations. You're saying this can't be an adversarial process.
It absolutely cannot. You must approach the authority, having jurisdiction as a partner in achieving public safety. That's the key. You present your surgical scope assessment, your equivalency analyses, and your phase compliance options as one comprehensive, well-researched path forward. The quality of your documentation becomes your legal leverage.
And the final step, step 5.
Step 5, which is paramount for institutional leadership, is to quantify the cost and schedule trade-offs with total transparency. The owner has to be given clear, objective data. Option A, full compliance now. That adds 15% to the budget and delays the project by 6 months. Option B, phased compliance. That maintains the schedule and the current budget, but it requires a dedicated maintenance fund for post-occupancy work and some political sign-off. In a mid-project crisis, transparency is the only antidote to public and political risk. Managing code evolution is less about design, really, and more about high-stakes leadership under pressure.
That deep dive into managing regulatory risk on just a single building, it requires immense foresight. But when we scale up and look at governments structuring these 20 or 30-year mega projects, that risk must multiply across decades and dozens of sites. How does that management strategy scale?
That's where we see a shift in mindset. We go from managing projects to managing programs, especially at the metropolitan scale. This insight is really driven by what we're seeing in these massive multi-decade urban developments in the Gulf and parts of China and India. They aren't defined by a single blueprint. They're defined by a 20 to 30-year construction program with constantly rotating design scopes.
So what's the fundamental difference in the governance structure there?
Program governance replaces project control. A project is transactional, right? It has a fixed scope, a fixed budget, and end date. A program is continuous. It requires institutional stewardship. The leadership team's job isn't to finish one building, it's to maintain momentum, to absorb global economic shocks, and to adapt the design vision to geopolitical shifts over, 3 decades. This requires them to establish adaptive design standards, a kind of living code for the whole program that guides all the smaller constituent projects.
So it's like designing the entire infrastructure around the basic assumption of constant managed change.
Exactly. And that constant change includes economic volatility. Which brings us to the next point. Engineering for supply chain instability. Given all the global disruptions we've seen, pandemics, trade wars engineers simply cannot rely on material availability or stable pricing anymore. And the solution we're seeing is the adoption of material-agnostic structural systems.
Material agnostic systems. What does that mean? Does that mean the structural design is so robust that the team can literally swap the primary vertical load-bearing system? Switch between steel, reinforced concrete, or even a hybrid solution, even after the foundation is poured?
That's the goal, yes. The design intent focuses on performance and geometry, not on a specific material specification. Now, this requires incredibly sophisticated coordination, especially in the connection detailing. But imagine the price of structural steel spikes 40% because of global tariffs. The procurement team can just pivot to a post-tension concrete slab system. Why? Because the core geometry and the foundation capacity were already designed from day one to handle the load characteristics of either solution.
But that has to be enormously complex, switching material mid-design. A steel frame needs certain clearances, connection plates. Concrete needs totally different rebar placement, formwork. Are you sacrificing short-term efficiency for that long-term supply resilience?
Absolutely. You are accepting a slight efficiency hit up front to gain massive economic flexibility later on. Structural flexibility becomes a form of economic risk management. The material selection stops being just a design decision. It becomes a procurement hedge against the futures market.
And this level of risk management, I assume, extends into the contracts themselves. You mentioned financial construction management, CM, as risk hedging. How are large public owners using CM contracts to hedge against long-term inflation?
Standard construction contracts are just incredibly vulnerable to inflation over multi-year projects. So advanced public owners, especially those running these huge metropolitan-scale programs, are using CM contracts that are basically financial instruments. They're designed to share and mitigate inflation risk.
Can you give us a concrete example? How does this hedging work with index materials or shared escalation clauses?
Sure. Let's imagine the cost of high-strength cement goes up 20% in 2 years. That's far beyond any standard inflationary assumption. Under a normal fixed-price contract, the contractor eats that massive loss, and that often leads to project delays or even bankruptcy. But under a hedged CM contract, we've indexed the price of key materials like cement, rebar, copper to a standard agreed-upon commodity inflation index.
You know what, exactly.
Meaning, if the price increase stays within a certain range, let's say a 5% index range, the contractor absorbs it as a cost of doing business. But if it exceeds 5%, the shared escalation clause kicks in, and the owner, the public body, shares that excess risk with the contractor. This ensures the contractor can keep working without facing financial collapse, and it ensures the 30-year program doesn't stall because of a temporary spike in commodity prices. The CM professional's role shifts from being a scheduler to being a financial forecaster and a risk broker.
That's a profound change. It turns CM into a systemic financial discipline, essential for the largest public works. Shifting gears a bit to the city level, this kind of systemic thinking is also reshaping zoning. We're seeing this move towards performance-based entitlement.
Right, we're moving away from the old prescriptive use-based zoning, residential here, commercial there, and we're moving toward rewarding buildings for what they actively contribute to civic resilience.
I get the goal, but what is a performance metric in practical terms?
Performance metrics are measurable contributions to public infrastructure. So instead of the city just dictating a maximum height, they offer zoning bonuses like extra allowable density or more height when a developer can prove their building has superior performance in an area of civic need.
And what are some of those needs?
Stormwater attenuation is a really common one. If your design manages 100% of its site runoff and contributes zero stormwater to the municipal system, you get a density bonus. Others could be grid stability contribution if your building can provide emergency power back to the local grid during a blackout. Or maybe superior waste heat recovery that services a neighboring public facility like a school or a library.
So you're essentially harnessing the private development budget to fund public infrastructure resilience, which leads to the ultimate challenge you mentioned, proposing a novel zoning metric where structural or energy performance directly increases your allowable density.
This is the high-level application of that idea. Let's focus on structural performance for a second. Instead of rewarding a building just for meeting the minimum code, what if we reward a building for proving its inherent structural capacity to withstand an extreme event? Let's say an earthquake that's 25% larger than the mandated code level.
And the structural engineer has to provide the analysis, the justification, that legal brief again, to prove that superior performance.
Exactly. And what's the civic benefit? The civic benefit is this. Post-disaster, that building doesn't become a long-term economic drain or a housing liability. It remains functional, it allows for rapid reoccupancy, and maybe it can even serve as a local recovery center. The city rewards that contribution to civic resilience with increased density. It ensures that market incentives are actually serving systemic, long-term safety goals.
It's designing robustness right into the market incentive structure itself. That makes perfect sense. Okay, we've covered regulation in finance. Now, here's where it gets really interesting, I think. Let's look at the hidden loads, the non-intuitive loads that structures now have to account for. These are loads driven by chaotic human behavior, by complex system interaction, not just the standard calculations for gravity and wind.
This section really gets into the depth of modern structural analysis. Advanced practice means you have to consider the full spectrum of operational reality, and that includes moments of social and political stress.
Let's start with maybe the most provocative concept the sources brought up, the structural implication of democracy.
This requires public institutions, we're talking city halls, capitol plazas, courthouses, to specifically analyze what we're calling structural allowances for civic protests. The standard assumed crowd loads in the code often severely underestimate the dynamics of high-density, coordinated public assemblies.
But wouldn't the code's uniform live load calculation say 100 pounds per square foot cover a large crowd?
It covers static weight, evenly distributed. It does not account for the kinetic energy of a surge or the high, non-uniform momentary load concentrations you get when hundreds of people move rhythmically together or surge toward a barrier. And beyond that, these crowds can generate significant lateral loads forces pushing horizontally on parapet walls or the edges of cantilevered structures.
Wow. So the designer has to account not just for the static weight of 1,000 people on a plaza, but for the momentary overturning moment created when 800 of those people surge onto the last 5 feet of a cantilevered balcony all at once.
That's the structural challenge, exactly. Public safety requires designing foundation stability and lateral bracing specifically to resist these localized dynamic forces that are inherent in high-density civic assembly. You're building the physical capacity for civic life, and you're acknowledging that democracy itself exerts physical pressure on the built environment.
That is a critical expansion of what we think of as structural responsibility. Okay, moving indoors, let's talk about operational density. What is Q-induced live load concentration in transportation buildings?
Think about any highly regulated choke point, an international border crossing, airport security, stadium ticket entry. Human behavior dictates that the density is never uniform. People form tight, sustained queues right near the processing point, and that's followed by large empty spaces immediately after they pass through.
So the load isn't spread evenly across a 300-foot-long baggage hall. It's highly concentrated in a few, say, 20 by 20-foot queue zones. And it's sustained there for hours, maybe even entire days.
And that concentrated, sustained load can be significantly higher than the standard live load assumption for that area. This requires specific, localized reinforcement for punching shear in those floor slabs, especially around heavy equipment like body scanners or turnstiles. The location of the expected queue, which is driven by human impatience and system flow, that governs the localized structural design, not the building's overall function.
And that's related to security decisions, too. This idea of security-driven load reconfiguration.
This is about anticipating management decisions made years after you've handed over the keys. If the management of a public atrium decides they need to install temporary heavy concrete or water-filled steel barriers or robust security checkpoints, the engineer has to ensure that the floor slab can handle that concentrated, often fixed load without any distress.
So the structural flexibility has to accommodate the defensive posture of the structure, even if that posture was never part of the original architectural program.
Correct. We have to design for the possibility that large, heavy objects will be temporarily or semi-permanently placed anywhere in that public space to mitigate some future risk, changing the load demands dramatically.
All right, let's shift to system interaction and aging, where the stuff inside the building dictates the structural performance. Let's tackle utility rack seismic interaction in laboratories.
This is a really crucial detail for specialized facilities. We often model the non-structural utility racks, the things that carry critical systems like gas, water, power, as just simple weight. But if those racks are designed to be rigid and they're bolted firmly to the floor slabs, they can act as a massive structural accelerator during an earthquake.
How does the rack system transfer that force?
Well, if the rack is stiff and it's securely attached, it essentially transfers the acceleration forces from all of its heavy contents directly into the floor slab. It creates a massive momentary point load. This localized force can be amplified significantly. It can change the natural frequency of the floor and can actually end up governing the final seismic design of the entire lab structure. The building has to be designed to withstand the violence being transferred by the very contents it's supposed to protect.
So that means the structural solution has to be coordinated with the mechanical and piping engineers to decide if the rack should be isolated or flexible or rigidly integrated, depending on the seismic region.
Precisely. If isolation isn't feasible, then the structural engineer has to design a floor plate that can handle the specific localized accelerations dictated by that rack's weight and stiffness.
Speaking of performance and history, this idea of the structure's memory is really powerful. Tell me about hidden corrosion stress memory.
What's fascinating here is that structures, they remember their environments long after the conditions change. When we assess an older structure for adaptive reuse, we can't just check for current corrosion. We have to study the structure's past exposure history.
What kind of history leaves a memory like that?
It could be a past localized chemical exposure, maybe a leak from a roof system 40 years ago, or a localized spill of de-icing salts. Even if that area is now dry and patched up, that past corrosion might have initiated microcracking or a localized reduction in the material's cross-section. This stress memory reduces the material's remaining capacity to handle new loads, even if the current conditions seem totally benign.
So you're designing against a ghost of past environments. You're recognizing that the material has a historical debt that reduces its current safety factor. You have to reclaim that capacity responsibly.
Exactly. It requires aggressive non-destructive testing, NDT, to map out that historical stress profile before you can approve any new loads.
Let's discuss vibration fatigue from external infrastructure. Why is long-term, steady microvibration from a nearby subway or a freight line, why is that often more dangerous than a rare, high-magnitude earthquake?
This is the difference between strength failure and fatigue failure. A rare, high-magnitude load like an earthquake, it tests the ultimate strength of a connection. It pushes the material to its yield limit. We design for that material to yield, but not to break.
But vibration fatigue is different.
Very different. Vibration fatigue, which is driven by millions of tiny low-amplitude cycles, it attacks the endurance limit of the material. Loads that are far, far below the material's yield strength can, over decades, initiate and then propagate microscopic cracks. This happens especially at welds, at bolt holes, at connection points. The structure slowly, relentlessly just wears itself out.
So steady vibration is like a relentless killer because it slowly compromises the material's integrity. It can lead to catastrophic failure years or decades later, even without a major incident acting as a trigger.
Right. The structural engineer for any transit-adjacent building has to spend significant effort designing connection details that are specifically resistant to these endurance limit breaches. They'll use detailed finite element analysis, FEA, to make sure those microvibrations are absorbed or dampened before they can start propagating cracks. This adds complexity and cost to every single joint.
Okay, now let's look at loads from future upgrades and use cycles, starting with vertical transportation. Elevator modernization, load drift.
The vertical transportation core is the spine of any high-rise. So when a building undergoes an elevator modernization, say you're replacing hydraulic lifts from the 1980s with heavy high-speed traction systems, the new equipment is a lot heavier. We're talking larger motors, heavier cabs, much heavier counterweights. It substantially increases the fixed load on that core.
And that modernization shifts the center of gravity and increases the static load on the structural core significantly, often way beyond what the original design parameters were.
So you have to design the core with the expectation that the heaviest element in it, the vertical transportation, will inevitably get heavier, faster, and more robust in the future. The reserve capacity you build into that core structure has to account for this load drift. It has to anticipate future equipment specs that don't even exist yet.
That is pure anticipatory design. Now, what about the most cyclical load of all? Tenant rotation structural wear.
This is where we analyze bureaucracy or institutional management as a kind of cyclic load. It's especially true for long-term government leases or multi-tenant corporate towers. Tenants don't occupy a space cleanly. Every single time a new department or new corporation moves in, they demand a refit. New cubicles, new servers, new layout, and this involves repeated drilling of utility holes, re-anchoring new walls and furniture, localized demolition.
So the repeated abuse, the constant stress of renovation and refit, that acts as a cyclic load that stresses floor slabs and anchor points, and it reduces their long-term integrity and their capacity for future use.
It's wear and tear, just magnified by an institutional scale. The original slab design has to factor in a quantifiable number of these renovation cycles over its 50 or 75-year life. It has to ensure the material remains robust enough to handle the inevitable trauma of tenant rotation.
Finally, let's talk about temporary concentration. Why do industrial campuses have to consider program displacement loads during renovations?
This links your structural design directly to the construction management phasing schedule. Think about a large pharmaceutical lab or a heavy industrial facility undergoing a renovation. The expensive, highly specialized, and extremely heavy equipment. Things like freezers, CNC machines, specialized testing apparatus. You can't just remove it from the site. It has to be temporarily relocated somewhere else on the active campus.
Which means you're concentrating a massive amount of weight, which was originally spread out evenly, into a small temporary zone in an adjacent wing that probably wasn't designed for that density.
Exactly. So the structural engineer has to coordinate with the construction phasing schedule and essentially sign off on a temporary hyper-concentrated load, a load that might only exist for 3 weeks, but which could overload the receiving slab if it's not properly accounted for. The design has to accommodate the heaviest equipment potentially being temporarily stacked or concentrated during these periods of renovation. We have to design for the worst-case scenario dictated by the renovation plan, not just the eventual uniform use.
We've looked at growth, resilience, these complex loads. Now we're at what I think is maybe the most profound and conceptually challenging section, design for decline, or for managed change. We're talking about an architecture of subtraction and dignity under failure.
This requires a complete inversion of that traditional architectural assumption, that all buildings must be permanent and prepared for endless growth. We are now seeing entire nations grappling with the reality of demographic volatility.
Nations like Japan, South Korea, Italy, they're facing long-term population shrinkage. And they're commissioning buildings that have to be able to gracefully downsize or consolidate their functions over time. Architecture is shifting from an idea of permanence to one of demographic responsiveness.
Right. If a community knows it's going to lose a significant part of its population in the coming decades, the civic center or the school they build today must be able to shrink gracefully. It has to optimize efficiency and cost over just sheer size. The design has to minimize the economic drain of carrying all that unnecessary square footage.
That shrinkage creates immediate and really serious technical problems, particularly with life safety. We have to analyze what you call redundant vertical circulation loss.
Think about it. If you surgically remove 2 floors, or you decommission an entire wing because of reduced need, you might inadvertently eliminate a required egress staircase. Or you might violate the travel distance requirements for the remaining occupied core of the building.
So the challenge becomes designing safe, disappearing egress. How do you design an exit route that can be safely demolished or decommissioned without compromising the fire safety of the people who are still inside the reduced structure?
It requires meticulous planning and segregated systems. You have to use independent structural and fire-rated zones. The remaining core of the building must, at every single phase of subtraction, maintain full compliance with travel distance, fire separation, and smoke control. If an exit stair is removed, the remaining paths have to be demonstrably compliant. That often means temporary fire-rated walls, revised smoke management zones, until the demolition is complete and the remaining structure is stabilized.
Which leads right into the core design exercise here, the downsizing capable building. To design a building that's intentionally meant to get smaller over time, that feels like an anti-architectural prompt. It challenges the designer's ego.
It's the ultimate test of humility and foresight. And the constraints here are what make it so interesting. The building has to use permanent, high-quality construction materials, no temporary facades. And the structural logic has to make the removal obvious, not hidden.
Why does the removal have to be obvious? Why can't it be a discrete, hidden consolidation?
Because the final crucial constraint is the maintenance of dignity. If the subtraction is hidden, or if it tries to mask the loss of area, the remaining building just looks like a perpetually unfinished or decaying shell. It becomes a symbol of community failure. But if the structural logic is clear, maybe through repeating articulated structural bays or pre-stressed connections designed for surgical detachment, then the subtraction looks like a deliberate, controlled consolidation.
So as the building gets smaller, the remaining core actually becomes more focused, more monumental maybe, more appropriate to the community's new size. It's an architectural triumph of modesty, not a story of failure. It's designed to achieve dignity under managed transition.
It's an architecture of transition, not of permanence. And this applies directly to construction management. Let's look at construction management as subtraction. Here's the scenario. A government office has to remove 30% of its floor area over 8 years because of staff reductions. And it has to do this while remaining fully occupied and active.
That's a long-term, politically sensitive operational challenge. What's the critical workflow for that kind of slow, phased decommissioning?
Step 1 is identifying structurally independent zones. The original building must have been designed with clear structural segmentation so that removing one section doesn't compromise the vertical or lateral stability of the adjacent occupied section. This dictates the entire sequence of work.
And that segmentation had to be planned decades ahead of time, ensuring that shear forces and load paths are cleanly separated.
Then, step 2. Designing a reinforcement before removal logic. Before you even start the demolition of a wing, temporary shoring, or more critically, permanent reinforcement, often has to be installed in the remaining core. It has to absorb the forces that were previously resolved by the adjacent structure you're about to remove. You reinforce before you subtract.
Step 3 must be about phasing the demolition for off hours.
Exactly. Since the building is occupied, all the disruptive, noisy, hazardous, work core drilling, heavy machinery, it has to be meticulously scheduled during nights or weekends. This is to ensure staff safety, public access, and continuous service. Noise and dust control become paramount. You're talking about temporary, sealed barriers with independent filtration systems.
And step 4, which is non-negotiable, code compliance.
As we discussed, maintaining code-compliant egress at all times is essential. Every single phase of the reduction has to pass the fire marshal's review. You have to ensure continuous fire separation and travel distance requirements are met for the constantly changing footprint.
And beyond the technical execution, there's that huge element of political management. When a government office downsizes, it can look like failure or austerity. It can impact public trust.
So the final step is managing the public narrative of that reduction as transparency, not as loss. The CM team and the owner have to communicate that this reduction is a deliberate, responsible consolidation of civic resources. It's making the remaining services more efficient and more focused. Construction in this context is sometimes subtraction, and that has to be framed as a fiscal and functional improvement.
That's a fascinating synthesis of public administration and structural logic. Finally, let's briefly touch on designing for degraded conditions. Evaluating partial failure operability for emergency facilities.
Right. Critical emergency facilities, hospitals, command centers, data facilities, they simply cannot fail. They have to assume that a major event, whether it's seismic, fire, or political, will cause degraded conditions, and they have to maintain their core functionality. This means designing with high redundancy, distributed infrastructure, and structural designs that allow parts of the building to be entirely inaccessible or damaged, while the command or critical life support functions remain operational in independent structural bays.
And we see this necessity amplified in these incredibly complex projects like the Continental Rail plus Civic Interface Hub, CRCIH. This is a project that integrates multiple overlapping functions: rail, customs, migration services, where jurisdiction and movement are all layered on top of each other.
That project demands an architecture of transition where the structural system has to accommodate security escalation without spatial redesign. For instance, if the threat level changes from low to high, the building has to be able to harden its security posture instantly.
And how does the structure accommodate an escalation like that?
The walls and the floor plates have to be designed to withstand high-level security threats. For example, providing structural capacity for vehicle ramming in specific ground floor zones, or designing internal walls to contain blasts in areas that might only temporarily be used as secure checkpoints. The structural design has to anticipate the highest possible security threat level in areas of high civilian overlap. This ensures the building can transition from a passive civic space to an active, secure interface on demand.
It is the ultimate expression of designing an institutional interface, where the physical architecture supports evolving public administration logic and fluctuating security requirements. So what does this all mean? We started with anticipatory design, and what we've synthesized today from these advanced professional briefs is, well, it's that the most advanced architecture isn't about building beautiful objects anymore. It's about designing resilient, adaptive systems. Systems built to withstand not just natural disasters, but economic volatility, supply chain shocks, demographic shifts, and the evolving demands of civic life.
The core lesson for advanced practitioners is clear. You have to operate at the decision scale, not just the drawing scale. By analyzing future code retrofitting loads, designing material-agnostic structural systems, and accounting for the deep structural implications of democracy itself, you are building capacity for an unknown future.
We've explored how structures remember their environment through hidden corrosion stress memory, how bureaucracy can function as a long-term cyclic load, and the necessity of achieving dignity when you're designing a building that's intended to shrink over time.
We've established that true mastery really involves shaping institutional interfaces and systemic resiliency.
We've covered how structures remember their environment and how democracy has structural implications. The ultimate question for you to reflect on tonight, building on these concepts of shrinkage, dignity, and longevity, is this: what does architecture owe society when growth stops? Think about that structural and civic responsibility as you transition your own practice from project control to program governance.
That's a deep dive for the rest of your week. Thank you for joining us for this crucial conditioning session.
Until next time, keep building arguments, not just assemblies.